So as Olaf has already given a very nice introduction to this challenge here, the promises of AM is complexity for free, geometrical freedom, we can optimize and do whatever we want. But in reality, it's a little bit harder. And today I'm going to take a small toy example, and then we'll try to discuss different ways we can tackle this problem. So let's consider a very, very simple design problem. We're going to have a load out here, and we're going to fix whatever we make on a wall over here at 4 points with 4 screws. And now we're going to design the part that is going to connect these pieces together. So it's very simple so that you can keep your intuition about what's going on here. So what do? We get in front of our CAD program and we start to draw something. So we can draw something on the left, probably a bit heavy, and Olaf just told us get the material volume down because it translates to cost, not so much because of the material, but because of the build time. So we remove some more material and end up with a design on the right, and then we think this is pretty good. But this looks a little bit like something that we could machine, or we could cast, or we could whatever. And why is that? And I think there are 2 reasons here, and Olaf already introduced both of them. One is the thinking we have as engineers. We know what we want to do, and we have an intuition, and we have been working with problems like this for 20 years, so we do something that is kind of similar to what we usually do. And the other problem is the software side, because if you sit in SolidWorks or CATIA or something else, you're not really invited to draw roses and other things. You're invited to extrude something and drill some holes or boss an area. And all of these design tools that are sitting inside CAD software suites, they invite you to draw something that is perfect for drilling and machining and casting. So even though the design on the right is probably pretty good, we are not so happy because no one can see that we're going to 3D print it and it's just going to be expensive. So what do? Let's add some lattice structure, because lattice, that's impossible to do with other manufacturing paradigms. So now everyone can see that we have been 3D printing a very complex part, and lattices are strong and light, right? They are lighter and stronger than the solid part. So what we typically do is, this is not even going on in the CAD program, even though it's changing at the moment, but adding lattice structures to parts has been something you've been doing in your additive manufacturing, slicing and hatching software like NetFab and Magix. So it's not even sitting at the design engineer's desk, it's at the manufacturing side of things where you prepare your build files, then you add some lattice as an afterthought. But let's keep this thought for a while and try to discuss a little bit about lattice structures and how we can use them. So the first question you may have is, what type of lattice should I ask? And typically you can choose if you want some totally random lattice structure like this one, or you want a regular lattice structure. And the regular lattice structure, you can design your unit cell, and then you can do a BCC type of lattice or an FCC type of lattice and put it in there. And there are plenty of studies on metal printed lattice structures and compression testing them and finding good material properties, etc. And you can do this. But one typical problem is that if you take a regular lattice and you start to cut it into funny shapes, then you get a lot of loose ends, dangling bonds, etc. And this is actually why almost all of them do the shell core design, where they put a solid surface on top, because then you cannot see all these lattice rods that are just hanging here. Of course, you can do something about this. You can either cut them off, or you can take all the loose end and triangulate a surface and try to connect everything again. But this is a typical problem you'll hit with the current lattice design tools. The next question you may have is, how do I dimension my lattice? So both the size of the rods, but also the size of the unit cell. Should I make a really coarse lattice or a very fine lattice? If I make it too coarse, then I need to consider overhangs, which may need support, etc. Or I at least need a design that is a lattice unit cell design made for AM. On the other hand, if I made it too fine, and I think we see way too many fine lattice structures at the moment, you face some other challenges. So here's just a zoom in on a printed lattice, and one thing you may notice here is that we have a rod going here. It's 0.6 millimeter in diameter, and it's not a straight rod. I mean, the precision of the machines and the surface quality makes the rod go like this. And this is the perfect recipe for making stress concentration certain places, and which are going to be really good places for crack formation. And then what you get is actually pretty poor fatigue properties of your lattice structure. And that's just for testing the lattice. Then there are secondary problems like how do you do QA inspection of a lattice like this? Of course, you could CT scan it, but the CT software, when you're going to analyze if the lattice is good, is not really made for lattice structures either. And that's difficulties on the manufacturing side. Also on the software side, you have problems, and if time permits, I'll come back to this, because it turns out that if you have more than, say, 500,000 or 1 million rods in your lattice, then the rest of the software, Magix and NetFab, and the software you get with your machine, whether it's Concept Laser or EOS or whatever, start to fail miserably. They simply cannot load these complex lattice structures anymore. So lattices, we have challenges with slicing and hatching them, at least when they are very complex. We have challenges in manufacturing lattice structures, and then the whole story about it's lighter and stronger. You hear it a lot in popular newspapers, etc. is simply wrong, because when you start to remove material from a part, your part is not going to be stronger. I'm sorry to say it. And actually it scales a little bit worse than just linear scaling. So your part is going to be not even stronger per volume or per mass, but it's going to be a little bit weaker. So why would you want to build lattice structures at all? And luckily it turns out there are plenty of reasons to do this. It's just not your typical stronger argument that you hear. So you might want lattice structures because of thermal properties or because of acoustic or dynamic properties in the lattice. One thing I'll get back to is that lattice structures have superior buckling performance, so we'll get back to buckling in a moment. And also, if you're not really sure about what load is my part going to sustain, then lattice structures can also be a good compromise, because they kind of can distribute loads throughout the lattice structure, and we'll get back to this in more detail as well. So that's a very quick whirlwind tour of lattice structures, and now I'm going to talk a little bit more about topology optimization, which is a little bit a different design paradigm. So in topology optimization, you typically start out defining a design space. This is where my algorithm is allowed to place material. Then you define solid volumes. So this is where there has to be material, because I'm going to mount my part. And then in topology optimization, it's an iteratively finite element calculation where mass is moved around until it's sitting at the perfect place. So the computer simply spits out an optimized design, fulfilling your design requirements. But also topology optimization has certain challenges when you try to use it. So one of them is that topology optimization is a computationally hard problem. So what you see if you use commercially available topology optimization software is typically you need a big computer, but it's still a difficult problem. So and these software vendors, they want you to be able to solve it on your own desktop computer or your own small computer. So they have to take shortcuts. One of the shortcuts they take is that they make the underlying finite element mesh rather coarse. So we have a coarse finite element mesh. And the other shortcut they take is the iterative process. They try to take big steps. And this actually leads to designs which are not really, they are very good guideline for where you are going to take your design. You can be inspired by it. In some cases, you can even use it after heavy smoothing. But in principle, there's a lot of manual post-processing on the design side you have to do. So here I have three different examples of the same design problem. Here it's what I would call a coarse or intermediate resolution. And one thing you'll notice here is that some of the thin rods here, they only have a few voxels or a few finite elements across the cross section. So that's actually not very good for your finite element calculation. The other thing you see is that it's rather coarse. It's a little bit difficult here because the screen is smoothing the part for us. But actually it's a little bit like building a part with Lego bricks, and you need to smooth out some of these steps from the mesh. Then we can try to say, fuck it, we take a big computer, a high-end, maybe a small cluster or something, and run it and see what we get if we do it the best way. So we take small steps, we use high resolution. And then you get a design like this over here. And you see something very interesting happening here. First of all, a lot of these rods have disappeared and turned into walls. And this is actually a bit surprising for most people, that this is a fundamental change in the design. But actually, when you use your intuition and think about how forces are distributed, if you have several load cases, then a wall is able to carry forces in different directions, where a rod is only really good at transferring forces along the direction of the rods. So here we are actually taking much better advantage of the material that is in the design. This part here is run with a voxel size of 1/10 of a millimeter, so that's more or less the precision we can build with our metal printers at the moment. So when we run an optimization like this, then we actually exploit the entire design space of the 3D printer. Of course, we don't want rods and walls that are 1/10 of a millimeter in size, because that's not really stable when you try to manufacture it on the machine. So then we impose a small feature size constraint and punish designs that have features smaller than our minimum feature size. In this case, it's 1 millimeter. And then something funny happens. If we still stay at the high resolution but increase the feature size, then this wall is maybe 1.5 millimeter thick, so it's not allowed anymore, so it's punished, and then the material starts to contract into rods again, and we end up with a design which is more resembling this over here, but now in a much more controlled manner, because now we are exploiting the design space and the capabilities of the printers, and we end up with a really nice and smooth design which is ready for 3D printing because it's optimized and designed at the same resolution as the printer. So then something I see a lot in medias at the moment is that we topology optimize a design, and then by some kind of post-processing we magically introduce a lattice structure again, because now we have a topology optimized lattice structure. And I've written careful, and my colleague said, that's too polite, you should just say no, don't do this. Because the topology optimization has already optimized with the material properties you've supplied it in the beginning, and now you're suddenly changing the design problem without informing the algorithm, because people are printing stuff like this. So this is a big no-no. But one thing you can do is to introduce another material in your topology optimization and say, okay, so my topology optimization can put solid material where it wants to, and it can put a lattice structure where it wants to, with lower density and with lower strength, and then play around with this. And now I'm just going to show you two examples done by my colleague Anders while he was doing his PhD. It's not the exact same design problem, but it's something similar. And in these images up here, blue means solid material and light gray means lattice structure. And the full dense design, if there's no lattice structure, looks like this. And then if we gradually increase, the mass is kept the same across all these designs, but we change the density of the lattice, and then the design changes. So there's the exact same mass going into this part. And what you see is that we get some lattice structures inside the volume. So we're a little bit back to some of the shell and core design concepts you see in Magix and NetFab. And why would you want to do this? one of the good things about doing this is that in topology optimization, you need to know the problem really well, because you define the forces and where you fix it, and then it optimizes towards this. But it doesn't take into account uncertainties in you. If you don't really know the design problem, if you don't know how big the force is or precisely where the force is going to be applied. So, and this is something we can try and test here. If we first look at, so it's good to be around here. These are, if we apply, we make these 5 designs, and then we test it where we apply a force exactly as it was optimized to be, and all of these designs perform more or less the same. But if now we only apply the force at 1/2 of the part here, so it's optimized towards this load case, but if we now test how will my part perform if the load case is like this one down here, where I only apply it at 1/2 the length here, then you'll see that my totally solid design performs much worse. It's better to be low. So this is this one here. But as I increase lattice structure, the performance closes in on what we try to optimize towards. So this means that if our actual real-world forces our parts are going to see are different from the design case, then this design is in some sense more robust towards these variations. Another good thing about lattice structures is the buckling I hinted at earlier on. Here you see a similar design where it's designed solid and designed with a lattice structure infill. This is just a 2D design problem to illustrate it. Again, it's the same mass of these 2 parts. You'll see that it's become slightly thicker here, but then lower density in the middle. And the buckling load of this part is around 30 Newton, and the buckling load over here is 5 times as high. So if you have a design problem where you know buckling is an issue, then lattice structures might again be very valuable. So just to recap a little bit, in topology optimization, resolution matters. If you run your problem high enough and don't take any shortcut, then your design is already smooth, so you don't need to do the manual smoothing. You have tens of thousands of points per surface, so it's much easier to fit a NURB surface or something if you want to go that road. You resolve your ruts, etc. really good, and there's no disconnected elements left. And we could even start to see hollow ruts. And then we very often see these wall structures formed. And this is actually something we are very happy about seeing, not only from the part performance perspective, but also back to the support issue that Olaf raised, because it's actually often much easier to make support for a wall, because you can almost always find a direction where the wall is self-supporting. So Olaf, would you rather remove support from a part like this or from a part like this? So that's a secondary benefit here. And just to point a little bit into the future, we can actually increase the resolution more and more and more. And this means that topology optimization is no longer only something you can apply to a small bracket or a small part here and there. This is a study that is going to be published in Nature in 2 weeks' time, where my other co-founder and colleague, Erik, studied an entire wing from an aircraft. He did it with 1 billion finite elements, so iteratively solving 1 billion element finite mesh. That means that this wing, each element is at the millimeter scale, so he's optimizing an entire wing on the millimeter scale. And you start to see a lot of the same features that we already discussed between thin walls and ruts when there's not enough material for the walls anymore. And out here, these ruts actually align as well, but there's just not enough material to form a wall. So this is a small printout of just a section of the wing, but you can look up the article very soon. But this means that we don't have to apply topology optimization to just small parts here and there. We can start to think about entire structures. So And then a very quick introduction to our company. Adimant, we are 3 co-founders in Adimant. We have been running the company in 3 years now. Primarily customers in space and aerospace, because as Olaf said, cost and stuff like that. We help them with topology optimization, so doing it right. We help with lattice design structures when the lattices become really big, or if they need to optimize lattices for certain performances. And then we help them with file preparation, because it turns out slicing and hatching is a little bit more difficult than it looks like. So I'll just give you 3 examples. One example here is topology optimization applied to an injection molding tool. So this is totally out of, normally topology optimization is applied to aircraft things where weight is critical. But in this case, because we can get a smooth design that is ready to print, we can actually start to think about applying topology optimization to more everyday problems. And in this case, the company had been printing this injection molding tool for 10 years with conformal cooling channels and everything. And they have just been printing it because that's how they always did. And then we tried to remove material with topology optimization. So this is the back side of the tool, so there's no function here. We just removed excessive material. And we could remove 50% of the material very quickly by running it through topology optimization. And then we end up with a part like this, and that's the build time that is important again. Lattice structures, we have helped tileless and linear space, slicing and designing a very big lattice, so close to 500,000 rods. I wanted to show you a 7 billion rod lattice for another aerospace company, but I'm not allowed to do it yet. But this is some of the work we do. And it turns out with slicing and hatching, it becomes complex when you have millions of rods, because the machines cannot really. So for example, some machines, they would load in 1 layer at a time, look at all the contours, and then it will start to calculate the hatches, so the actual laser motion. And this can be time consuming when you have thousands and thousands of polygons. So I had a case where they could shoot the layer in 5 minutes, as in Olaf's case, but it took 25 minutes for the machine to calculate the paths for the next layer. So that meant that what was meant to be a 20-day build job turned out to be a 3-month build job, because that's just how the software works. It calculates these tracks online because you don't want to waste hard disk space. So we do some reverse engineering and tricking of the machines to get them to build what we want them to build. And then as just a very small, because we are working with big and complex data, we actually also apply to STLs and helping people repairing stuff. So this is just a small architecture example where you have some architecture sitting in SketchUp drawing a house with 917 shells, disconnected shells, and open most of them. And then we connect them into one shell and clean up all the boundary edges. And then when we scale it down, a lot of these features are going to be too small for the printers, so then we selectively scale up just the small parts to the minimum feature size of the machine. So that's another thing we do. So that was my introduction to topology optimization, lattice structures, and our company.
Thank you so much. Thank you so much. So it's not just about optimization, it's also to know what you optimize for, I hear you. But how often does it happen that you get these, whoops, not 20 days, 3 months? How often is it that you still have this learning experience, so to say?
We get requests like that a couple of times a year, and it's only through our network that people are talking to each other, because we are not really advertising that we slice for people, because everyone believes they can slice themselves. They bought Magic, so. But from time to time, we have companies that get data that are so big that the software cannot handle it anymore.
So it's a greenfield in some senses, but you're mature in some senses, and there's still a lot of development to do. Really good to hear you talk. Thank you so much. Thanks.